Conformations of alkanes. This part in chapter 3 talks about how to view the stability of alkanes using a known projection that is called Newman projection. This Newman projection, it takes practice to be able to draw Newman projection for any compound that we're going to be dealing with. And that compound is an alkane structure. We're going to learn later on today how to do conformation of a cycloalkane. That's going to be slightly different how we're going to do it than the one that we're going to be doing for alkanes. So looking at this molecule, which is ethane, usually the Newman projection, it's a representation of a bond within the molecule. In this case, it's the bond between the two carbons. And the way how we put this bond in the Newman projection is by putting a circle and a dot in the middle. This dot in the middle, that represents the carbon, one of the two, doesn't matter which one you put in the front. And the second carbon would be basically behind it, something that you wouldn't be able to see. But you would assume that the circle is basically gonna have the bonds of the backside carbon. So you have the carbon in the front with 3 bonds attached, and the carbon in the back, which is attached to the one in the front, and the remaining 3 bonds of the backside carbon would be basically the ones coming off the red ring in this case. So this circle, once again, it's going to have both carbons in it, one in the front and one in the back. This Newman projection is going to have 4 types, 2 that are staggered and 2 that are eclipsed. What's the difference between the two? The eclipsed usually is when you have the 2 bonds coming off both carbons to be on the same face, meaning right behind each other. So you see clearly that this eclipse, or this eclipse, which is obviously the same in this case for ethane because there are no substituents coming off those 2 carbons, you will always see that these hydrogens are right behind each other. And that's why this type of Newman projection would be the eclipsed Newman projection. The staggered, you're going to have more space between the 2 groups coming up of those 2 carbons. So the carbon in the front and the carbon in the back, you're going to have the substituents or the atoms connected to them are not behind each other. They are further apart from each other. So there is some sort of 60-degree bond angle between those atoms or those groups. Now keep in mind, we don't have a control over which conformation we're going to be forming or we're going to be having for a molecule. There will always be a rotation of 60-degree to go from one to another. So if you start with the staggered, you're going to go next to the eclipse, and you're going to do next the staggered, you're going to go next eclipse, and so on. So they will alternate. Even though the staggered in all compounds, all alkanes, will always be more stable than the eclipse due to the less steric hindrance, less steric interactions. When you have the 2 groups away from each other, obviously will be much more stable than having groups right behind each other, right on top of each other, interacting with each other. So that's why you will always see the staggered gonna be much more stable than the eclipsed, regardless what type of eclipsed it is, regardless what staggered type it is. It will always be the staggered more stable than the eclipsed. All right, so what's happening here, as you see for the ethane molecule, you will see a rotation of 60-degree. So this carbon in the front is the one that's being rotated, and that's something we're going to have to keep in mind. When we rotate an sp3 cc bond, we're always going to be rotating one of them, keeping the second in place. And it doesn't matter which one you rotate, and it doesn't matter which one you keep in place. Just keep in mind that you're going to always have to rotate one of them. So in this example, they rotated obviously the black, which is the front carbon. So this hydrogen will be rotated 60-degree, so it goes right here. This hydrogen will be rotated 60 degrees, so it's going to come right here. And this hydrogen right there will be rotated also 60 degrees, so it's going to come right in the middle between the 2 hydrogens that are coming off the back carbon. So that now is the staggered conformation. Next would be an eclipse resulting from another 60-degree. So now we have a total of 120-degree considering the starting point. So this will now go right behind the one in the front, and this hydrogen will go to the pink hydrogen right there, and this black hydrogen will go also behind that left-hand side hydrogen. So now you're having an eclipsed conformation again. Now these two eclipsed conformation will be the same in terms of stability and the same in terms of energy as well. So that's why there is no difference between the two. And that's why we won't have a second eclipsed type for this example. We will look at another molecule that's butane, where we're going to see the two types of eclipse, and we will also see the two types of stagger. Here's another 60-degree rotation. So now we have the 180-degree of the two hydrogens that there were 0 dihedral angle, the first conformation. Now they are 180-degree from each other. So we could see clearly now that we're going from an eclipse to a stagger. So they will always alternate, as I mentioned. Now, these conformations will basically always result out of a 60-degree rotation every single time. And room temp will be enough energy to provide to those conformations to alternate. So what we're trying to say here, if we cool the molecule at very low temperature, we may have a selectivity to control what conformations we're going to make, which usually are the most stable ones, not the least stable ones. So let's look at butane, as it is easier to visualize both types of staggered and both types of eclipse. Now, if I look at the very first one, this will have basically the viewing of the C2C3 in this butane molecule. C2 is the one on the front, C3 is the one in the back. As we say that this circle will have both carbons in it. The one in the back is going to be hard to see here, but it's basically the one that's going to have the bonds coming out of it, which is the methyl and the two hydrogens. And the one in the front that you can see clearly the 3 bonds coming out of it. All right, so what do we have here? We have a C2C3. We know that C2 has a methyl and has 2 hydrogens. And that's what we have, a methyl and has 2 hydrogens. And the one in the back, you can see clearly that we're also going to have methyl and 2 hydrogens. And that's where they are. Now, how come we started with a total eclipse? Well, the totally eclipsed is basically when you have the 0 dihedral angle between the biggest 2 groups coming off the 2 adjacent carbons. So here are the 2 adjacent carbons, C2 and C3, and the biggest group of carbon number 2 will be the methyl, and the biggest group of carbon number 3 would be also the methyl. When you have the biggest 2 groups on an eclipsed conformation right behind each other with a 0-degree dihedral angle, that will be the total eclipsed conformation. That's the least stable, most energetic conformation due to the steric interaction between the 2 bigger groups, the 2 biggest groups of those 2 carbons, C2 and C3. Now, keep in mind, every single time an eclipsed conformation is formed, the next one is expected to be a stagger. Once the stagger is formed, eclipse would be next to be formed, and so on. So they alternate, keep that in mind. And that alternation will be resulting from a 60-degree rotation. So the next 60-degree rotation will be basically placing the front carbon in a way that the methyl will go to the right-hand side, and that's what you see here. This hydrogen will go down here, and this hydrogen will go right between the 2 groups coming off the back carbon. Now, this molecule, this conformation now, is a type of staggered. What type is it? It's the gauche staggered. So gauche or gauche, both are acceptable to say. That will be when you have the 2 biggest groups of the 2 carbons that you are viewing in a Newman projection that are 60-degree away from each other. So you can see here clearly that there is no steric interactions compared to the eclipse, to the total eclipse. is still going to be more stable, but you will have something that's more stable than this. And we're gonna see that in a minute. Now, this gauche staggered will have a 60-degree rotation to result in an eclipsed conformation, as we see here. Now we're going to have this methyl behind this hydrogen. That's what you have here. This hydrogen will be behind the other hydrogen, and this hydrogen, the one in the front, is going to go behind the methyl. So you could see it clearly that how it is actually the steric interaction got increased going from a staggered to an eclipsed. Now this eclipse is not going to be the total eclipsed one, due to the fact that the two biggest groups of those two carbons, they're not right behind each other. They are actually further away from each other. So this eclipsed will be more stable than the total eclipsed, but both eclipsed will be less stable than any staggered, whether it's a gauche staggered or what we're going to see next, which is the anti-staggered. So this eclipse, which has basically the 120 degree now between the two methyls that we are tracking from a 0 dihedral angle to 60, now they are 120. They're going to go through another 60-degree rotation. This 60-degree rotation now is going to place the methyl on the front carbon to be right here, and that's what you see, 180 degree from the other methyl. So this methyl is going to come right here. This hydrogen is going to go in between the two, and this hydrogen is going to go between the other two groups. So what do we have here? We have an anti-staggered. The reason why it's anti, because the biggest two groups of the two carbons that we are viewing their bond in the Newman projection are farthest apart from each other. And that is the reason why this conformation will be the most stable, least energetic. Most stable, least energetic, which is the anti-staggered. It's not appropriate to call it gauche, because the gauche is not the one that's going to have the biggest two groups away from each other in 180 degree. The other one should look like this in order for it to be called gauche staggered. So once again, the total eclipsed and the eclipsed, these two are less stable, more energetic than the other two staggered, the gauche and the anti. Now, keep in mind that when you are asked a question about energy diagram, the highest points are usually the one that's going to be more energetic than the lowest points. So if I start with the 0 dihedral angle between the two groups, I will see it the highest in terms of energy. Why? Because of the steric interaction between the two. This steric interaction between the two methyl groups makes the molecule to face high energy value, less stability for it. So next will be 60-degree rotation, having the staggered, which is gauche in this case. This will be much more stable than the total eclipse, less energetic. What would be next? The eclipsed, where you're going to have basically the two methyl groups that are not behind each other, but there is still interactions between the hydrogen and the methyl and the hydrogen and the other methyl, and that's what will cause the energy to be higher than the staggered. So this will be higher in energy, not as the energy of the total eclipse, but still higher in energy than the two staggered, the gauche and the anti. Here is the anti, where you're going to see the lowest in energy, most stable. So the two methyl groups are 180 degrees from each other. Next would be the eclipsed, where you're going to have the methyl. The first one was to the right, now it's to the left. And you can see clearly that these two are exactly the same in terms of stability and in terms of energy. So that's why you see them on the same level. So in terms of steric interactions, they are actually the same. Next would be another gauche staggered. This gauche staggered is not the same exact as this gauche staggered, because this one you're going to have the two methyls basically to the right. This two methyl is going to be to the left interacting. So the one that's resulting from the first 60-degree rotation will be the same in terms of energy and stability of having the 300 rotation. So you could see clearly that the two gauche stagger, they are the same in terms of stability, they are the same in terms of energy. Next would be going back to the first conformation where we had the two methyl groups, the biggest two groups and the two carbons, zero dihedral angle, and that's why you see it highest in terms of energy and in terms of steric interactions between the groups coming off the C2 and C3. So what's the conclusion out of the slide? The conclusion is that we're always going to have the possibility of existing or formation of four Newman projections for any straight chain alkane. This Newman projection will have the possibility of having a staggered that can be gauche staggered or anti, has the possibility of forming eclipsed or total eclipsed. Sometimes the total eclipse would be called syn eclipsed. Now, when you have the biggest two groups of this, the two carbons that you are viewing their bond, they are right behind each other in a zero dihedral angle, that will be the total eclipsed or syn eclipsed. Most energetic, least stable. When you have the two biggest groups coming off the two carbons that we are viewing their bond, in 180-degree dihedral angle between them, farthest apart from each other, that will basically be the anti-staggered conformation. That's usually the case for the Newman projection of alkanes. So if I have, once again, the two groups, I can see here clearly, if I have a longer chain than just 3 or 4 carbons, I should be just always asking you the question to focus on a certain bond, and that bond will always be what's on the circle. So this circle will basically be having the one in the front and one in the back, and that will be up your choice, which carbon you're going to put in the front and which carbon you're going to put in the back. And the remaining side chain of that carbon that's on the front, you will basically be placing it on any of these bonds. And the one in the back, once again, you will always place the side chain that's coming off that carbon to place it on any of these bonds. And if these two side chains are farthest apart from each other in 180 degree, that will be basically the anti. If they are in a 60 degree, whether to the right or to the left, that would be the gauche staggered. If they are right behind each other, that will be the syn eclipse or the totally eclipsed. If they are like this, where you're going to have basically the two biggest groups not right behind each other, however, they are behind other atoms that are connected to the other carbon, then that will be the other type of eclipse, which we call it eclipsed. Cycloalkanes. Hydrocarbon molecules, they have the chemical formula of CnH2n. If you remember alkanes chemical formula is CnH2n plus 2. So it costs the alkane 2 hydrogens in order to cyclize. The smallest ring or the smallest cyclic alkane would be the cyclopropane, C3H6. Next would be cyclobutane, cyclopentane, cyclohexane, cycloheptane. What we notice here, the smaller the ring, the more ring strain we're going to have. And this ring strain is coming from what we call the angle strain. What does angle strain mean? Every single carbon that is it's bonded to 4 atoms will always be an sp3 carbon and usually has a 109.5 bond angle. But when the cyclic alkane is formed, the smaller it is, the more the bond will be going through what we call angle strain. Angle strain is going to cause the cyclopropane, for example, to be 60 degree, not 109.5. The cyclobutane to be 90 degree, not 109.5. The Pentane would be about 104.5 or 105 degree bond angle. Cyclohexane would be more of relaxed, so you will see it actually getting close to 109.5. Even the cyclohexane is going to go through some conformations where one of them is the only one that's going to have a perfect 109.5 bond angle. So every single time we talk about angle strain, keep in mind that has to do with how much the bond angle is deviated from the ideal bond angle. In this case, for an sp3 carbon, the ideal bond angle is 109.5. The more deviated it is from it, the more angle strained the molecule. So when I rank those cyclic alkanes, I will always say this cyclopropane is the most strained. What is that supposed to mean? That means the most structure that's deviated farthest away from having an ideal bond angle. And not just that, there's another term that's called torsional strain. Torsional strain has to do with bonds being eclipsed. And we just learned in the alkane section where the eclipsed conformation will always be less stable, more energetic than a staggered conformation. So we can see clearly here, the smaller the ring, the more eclipsed bonds will exist in the molecule. Therefore, we'll have more torsional strain. So two ranking I could be asking you in regard to cyclic alkanes: angle strain or torsional strain. And they are in the same direction, meaning the smaller the ring, the more angle strain it is gonna have, and the more torsional strain, meaning eclipsed hydrogen bonds within the molecule. So that's important to keep in mind. In terms of naming, there are a set of rules that are very simple. If the cycloalkane has one substituent, there is no need to number the ring. So like in the example of methyl cyclopentane, I don't need to say one methyl cyclopentane. I don't need to mention one terbutyl cycloheptane. Okay. You can see here an example of a complex substituent. I will leave it for you to read, as I will not be asking you about complex substituents in this course. Now, when it comes to having two substituents on the cyclic alkane, the priority in terms of numbering the ring will go for the one that shows up alphabetically first. I have a methyl and I have an ethyl. Which one would go first? Ethyl. That's why the numbering will start from there. If I would have a terbutyl versus a methyl, terbutyl will be first. If I would have a terbutyl and an ethyl, terbutyl will be first. So keep in mind that you're always going to have the alphabetical order, what's going to determine the numbering if I have two substituents in the ring. So in this case, I'm going to have ethyl and methyl, so one ethyl, two methyl cyclobutane. What if I have more than two? If you have three or more substituents on a cyclic alkanes, always give the lowest numbering possible for the substituents. So whichever way it is that you're going to have to number the ring for the goal of keeping the lowest numbering possible for the substituents. So in this case, you have two methyls sitting on carbon and one methyl sitting on another. So you're going to have to give the lowest numbering possible for most of the substituents. So in this case, you will have number one here, as these two will be given number one, and this will be number three. So you can see here that is 1,1,3 trimethyl cyclopentane. Here's another example. So you have two ethyl groups sitting on one and an isopropyl sitting on another. So you're going to have to give this carbon to be number one, not this. So that way you end up having the lowest numbering possible for the substituents. Okay. So that's what we mean by numbering the ring based on giving the goal of or achieving the goal of lowest numbering possible for the substituents. Now, what if I have a chain and a ring attached to it, but the chain has number of carbons that are greater than the number of carbons within the ring? Like in this case, you have 3 carbon ring, and I have a side chain that obviously has much more than 3. The same here, and in that case, you will consider the cycloalkane a substituent. So it becomes a cycloalkene. As you see here, 4-cyclopropyl, 3-methyl octane. And it will be alphabetically ordered based on the C of the cyclo prefix. So it's not, it's a one word, So it's not based on the P of the propyl, it's actually based on the C of the cyclo. So here it is again, cyclobutyl versus dimethyl versus the M. So cyclobutyl will be first. You can see clearly here that you're going to have 1 cyclobutyl, 3,5-dimethyl cyclohexane. I have a cyclopentyl and a cyclohexyl. Which of the two is going to be the parent? Will be the bigger ring. So cyclohexane would be the parent name, and the cyclopentyl becomes a substituent. So now you have cyclopentyl cyclohexane. Cis and trans, it's a geometric isomerism. We visited this when we talked about alkenes in the very first chapter. We say there that when you have a rigid bond, such as a double bond or a ring, you will have the possibility of having cis and trans. Now, if the two biggest groups are across the alkene are facing the same side, that will be a cis. That same applies if I would have a ring. If the two biggest groups are facing the same side, there will be a cis. If they are facing the opposite side, that will be a trans isomer of that cyclic alkane. So these two molecules are not the same. These two molecules are actually stereoisomers of each other. Stereoisomers of each other. And that will have to always do with arrangement of groups in space. Arrangement of groups in space. So stability of cycloalkanes, as we mentioned, the cyclopropane would be the least stable, most strained, whether we're talking about an angle strain or torsional strain. It gets relaxed more and more you go toward the cyclohexane. We will be responsible for the most stable conformation of cyclohexane. You will not going to be asked about cyclobutane or cyclopropane or cyclopentane when it comes to conformations. Conformational analysis of cyclohexane is the only thing that you're going to have to be responsible for. Knowing how to draw a molecule in the chair conformation form, knowing how to figure out the stability of it, viewing it through the chair conformation. So cyclohexane will have several conformations. And the two most stable conformations are basically the chair conformations. So you could see here that the chair conformation will give a half chair, the half chair will give a twist, the twist will give a boat, boat will give another twist, twist is going to give me half a chair, and at the end give me the chair. You're not going to be responsible to draw any of the other conformations that are not as stable as the chair conformation. So you're going to only be responsible to figure out how to draw a chair conformation for any cyclohexane. Keep in mind, as we see here in the energy diagram, these two chair conformations are not the same. One is tilted to the left, one is tilted to the right. So these two, you could see clearly that they are resulting from the what we call ring flip. It's a 180-degree rotation that we call it ring flip. You could see how carbon number 6 is now becoming carbon number 1. So that's basically bringing the carbon at the bottom up, and that carbon number 6 now is going to the left. Carbon number 5 going further left. Carbon number 4 going down, and so on. So this basically tells me that these two chair conformations are not the same. They may have the same stability in some cases, but you may have one of them being more stable than the other. And that's what we're going to see in the examples that we're going to visit today. Drawing a chair conformations requires practice. It's very important that we take enough time to practice how to draw the skeleton of a chair conformation. And when it comes to drawing a chair conformation, you always have to be responsible for figuring out where the bond direction is. So here's a chair conformation where we see basically the 12 hydrogens of a cyclohexane. It's C6H12. So for every single carbon, you're supposed to have 2 bonds going to the 2 other carbons and remaining 2 bonds. One of them is a hydrogen that's axial, and one of them is a hydrogen that's equatorial. So if you look at the carbon number 1, you have 1 axial, 1 equatorial. If you look at carbon number 2, equatorial and axial. Carbon number 6, carbon number 5, any of those carbons, you'll always see the 2 types of bonds. One is axial and one is equatorial. The axial is due to the fact that it's directed vertically parallel to the axis. So you can see here the axial up, axial down, axial up, axial down, axial up. You could see an alternation here. One axial up on one, the next one would be axial down, the next one would be axial up, and so on. So hopefully that makes it easier for you to draw the chair conformation. So you could see all of these axial bonds are actually directed within the same direction of the to the axis of the ring. So the equatorial are directed basically outward toward the equator of the molecule. So you could see clearly here that equatorial number one, carbon number one, will be parallel to the bond adjacent, going in the opposite direction. Carbon number two, equatorial, parallel to the adjacent bond, going in the opposite direction. Equatorial, carbon number three, going parallel to the adjacent bond in the opposite direction. So that should right away remind you that since it's not parallel to the axis of the bond of the ring, that it means it cannot be the axial bond. It has to be the equatorial. Going onto carbon number four, you can see this bond is parallel to the adjacent bond, going in the opposite direction. Carbon number five, you have the bond again parallel to the adjacent. Either of the two adjacent will be the same, and to compare it to, and it will be basically opposite to it in terms of direction. So every single carbon, once again, we could extract out of this drawing that every single carbon is going to have one axial, one equatorial, and the axial ones, there should be no more than 6 hydrogens, and the equatorial bonds no more than 6 equatorial hydrogens. Now, the axial ones, you will always have 3 up, and you can see here C1 and C3 and C5. These are where the axial up bonds, and you will always have 3 axial down bonds. You can see here clearly C2, C4, and C6. These are the 3 axial down bonds. Equatorial, same thing. You're going to have 3 equatorial up and 3 equatorial down. The same alternation that we see in the axial, you will also see it in the equatorial bonds. So if you start with one that's equatorial down, the next one you'd be expecting to have equatorial up. Next one will be equatorial down. Next one will be equatorial up, equatorial down, and finally equatorial up. So you shouldn't have more than 6 equatorial bonds. 3 of them are up and 3 of them are down. So if I have a substituent on the cycloalkane, on the cyclohexane in this case, which is the methyl cyclohexane, how do I know where to place it? Well, first of all, the fact it's one substituent, it doesn't matter which carbon you pick. But keep in mind, if you pick a carbon where that substituent is up, it has to have a ring flip conformation where it's going to keep it also up, but in the other type of bonds. Meaning, if I have an axial up in one, which is the methyl that's axially positioned now, you're going to have a ring flip where the methyl now is an equatorial up. So that's the right way of doing the interconversion of one chair conformation going to the other. So you could see here clearly then this one is tilted to the right, this one is tilted to the left. These two are not the same. However, they result from a ring flip of each other. So the methyl that's up here, it's also up in the second, but this one is axially positioned, this one is equatorially positioned. So this is how we're going to always do the chair conformation. We're going to always draw both chair conformations, and if there is a substituent that's on one, being axial, is going to go equatorial on the second. Now, how do I know which carbon is going to go on next? Well, keep in mind, carbon number one, once we do the ring flip, is going to become carbon number 2. And carbon number 6 is going to become carbon number 1. So you're going to basically shift all the carbons to the right by 1 carbon. So carbon number 5, see here, Now it goes to where 6 is. Carbon number 4 goes up. Carbon number 3 goes to the left. Carbon number 2 goes to the center. And carbon number 1 that's up, it's going to go down here. So this is how we basically track that we did the rotation correct. So 2 things I want to make sure that you keep in mind. First, once you draw the 2 chair conformations, that's one tilted to the left and one tilted to the right, make sure that you have that substituent in the same direction. So the methyl or that substituent, if it's up in the first, it cannot be down in the second. It has to be up also in the second. And the second thing, if one chair conformation is going to have that substituent axially positioned, it cannot be also axially positioned in the second. It has to go equatorially positioned. So that's how it is. Let's look at another example. So here's the terbutyl. So that, or this is actually the methyl, sorry. This is the same example. We're going to see actually how come this chair conformation is more stable than the other. So this chair conformation, we're going to have the equatorial positioned one, and this chair conformation is going to have the axial positioned substituent. So this methyl is going to have clearly axial interactions between the other hydrogens. So this methyl, which is axially positioned, is going to allow for what we call 1,3 diaxial interaction. What does that 1,3 come from? 1,3 comes from having the carbon substituent or hydrogen interacting with carbon number 1. That carbon that is going to have the substituent is going to look for the third carbon. So not the second, the third, whether you're going from the top or you're going from the bottom, you will always see that carbon number 3 going to have a substituent or a hydrogen to interact with it. That's called 1,3 diaxial interaction. And this 1,3 diaxial interaction, it destabilizes the molecule or the chair conformation. This makes the molecule that's going to have 1,3 diaxial interactions much more than the other to be less favored. And that's why you see here the equilibrium is favoring the right-hand side. How come? Because when it's in the equatorial position, when you have the substituents on the equatorial position, you cannot minimize the amount of 1,3 diaxial interactions in the molecule. You're going to have some between the hydrogens, but that's not minimal compared to the substituents interactions. So having a substituent interacting with a hydrogen is going to have much more energy compared to hydrogen-hydrogen interactions. So the conclusion out of this, that every single time we have a cycloalkane or cyclohexane in this case, we're going to have 2 chair conformations. The one that's going to have the substituent on the equatorial position is going to be more favored. And you can see here clearly that is 1.7 kilocal per mole more stable than the other. So that's important to actually keep in mind. So the 1,3 diaxial interaction is always the factor that's going to determine the stability of the chair conformation. So we could see here how if I would change that X with any of these groups, the bulkier the group, the more energy it's going to have. So that clearly tells me if I have the choice between a bigger group and a smaller group to go equatorial, I will pick the chair conformation that's going to have the bigger group to go equatorial. So that will minimize the amount of 1,3 diaxial interactions. So you can see here another example of cis 1,3 dimethyl cyclohexane. Why is it cis? Because the 2 groups are on the same face. Now, once I draw the 1,3 dimethyl cyclohexane, I'm going to see clearly that I could have both of them up axial, or I could have both of them up equatorial. So there is a clear distinction between the 2 when it comes to stability. One of them is going to have great amount of interaction, that's called 1,3 diaxial interaction, and one of them is going to have none between the 2 methyl groups interactions. However, there will be hydrogen-hydrogen interactions, but this hydrogen-hydrogen interaction is going to be basically counted to almost nothing when it comes to energy compared to the 2 methyl groups. So that's why the diaxial interaction between the 2 methyl is going to make this molecule so unfavorable, or this conformation so unfavorable, and having the two equatorial positions method would be having that conformation to exist in more than 99.9%. So if I have a question on an exam and asking me to draw the most stable conformation of a cis-1,3 dimethyl, I have the choice of drawing both of them equatorial up or both of them equatorial down. So when it's not telling me what direction the two groups to be, I have the choice to place them both up or both down, because both of these conformations, whether I have both of them equatorial up or both of them equatorial down, will result in having that structure to be the cis structure. So the equatorial positioned one will be the most stable one. If the question is asking me to draw the least stable chain conformation of a cis-1,3 dimethyl cyclohexane, I have the choice to draw that both of them are up or both of them axial position down. So if I have that axial position basically on here and on there, that will also be accepted, because that structure is also going to be the cis-1,3 dimethyl cyclohexane. Here's an example of another substituted cyclohexane. In this example, we're going to have basically the trans. What is this chain conformation? Well, 1,3 dimethyl. So I have carbon number 1 has a methyl and carbon number 3 has another methyl. When I see the word trans, that means these two cannot be on the same phase. One is going up and one is going down. And when I do the ring flip of this chain conformation, since this one is tilted to the right, I'm going to have the one that's tilted to the left. This methyl is going to go to the next carbon, and this methyl is going to go to the next carbon. So this chain conformation is the ring flip of the second. All right. Which of the two is going to be more stable? Well, isn't it this going to have 1,3 diaxial interaction between the methyl and hydrogen, same as this methyl with the other hydrogen, also going to have 1,3 diaxial interaction? So what does that tell me? Having the same two groups, one of them axial, one of them equatorial in one, same two groups, one is equatorial and one is axial in the second, will result in having the two chain conformations to be the same in terms of energy and stability. So sometime you will have that scenario where you're going to have a chain conformation resulting in two conformations, and these two conformations will be the same in terms of 1,3 diaxial interaction. And this is important to keep in mind, that we didn't say the two don't have 1,3 diaxial interactions. Both of them do, but both of them have the same amount of 1,3 diaxial interactions, and that's why both have the same amount of stability and same amount of energy. Here's another example where we're going to have cis-1,4 diterbutyl cyclohexane. So when I see the word cis, that means they are both having the same phase. One is down and the other one is also down. So I could see here clearly that I'm going to have basically the other chain conformation similar to the dimethyl. I will also have the other chain conformations to be the same when it comes to stability of this chain conformations. Now, the moment it goes to a twist boat or half chair or a boat, automatically will have the chain conformations to be basically the one that's going to be more favored to draw. Just keep that in mind. Here's another example of another substituted cyclohexane. So we have 1,2 cis dimethyl. So the two groups basically having one is axial, one is equatorial, one is axial, one is equatorial. So that's why the two structures are going to be the same in terms of energy. Here is another substituted, disubstituted, where you're going to have the trans dimethyl on carbon number 1 and carbon number 2. One is going to have axial and the other one is going to be axial. The equatorial positioned one will be the structure resulting from the ring flip of the first. If this axial up in the first one is going to have to go equatorial up in the second. If this axial down in the first, it's going to have to go equatorial down in the second. So it's important to keep this in mind, that whatever axial position group on the first one is going to have to go equatorial position, same direction, up, up. If it's axial position down, it's going to also go down, but equatorial this time. Okay, If I look at the 1,3-diaxial interaction amount in this, is going to be much greater than the other. The fact that the two substituents are both placed axial automatically will have an amount of 1,3-diaxial interaction is going to be the top, maximum, compared to the other where the two groups or the two substituents are placed equatorial. So they're not going to have 1,3-diaxial interactions in regard to those methyls. They will have hydrogen-hydrogen interactions, but they're not going to have substituents interaction. So that's why this, in terms of energy, will be greater, will be more favored. Here's another example where we see trans 1-ethyl 3-methyl cyclohexane. What we see here, that when we draw the chair conformations of the first, this chair conformation, if we choose to have the ethyl and the methyl in a position where one of them is axial and the other one is equatorial, as long as they are both trans to each other, what does trans mean? They are not in the same phase. One is up and one is down. So I chose the ethyl to be up and I chose the methyl to be down. It's your choice. As long as you keep them trans to each other, that's perfectly fine. All right. The one thing you can keep in mind, if I put the methyl up on the first one, axial, it's going to have to go equatorial up, and that's what you see here. And the ring flip is going to bring it down here in the second chair conformation. If I chose the methyl to be equatorial down in the first, it's going to go axial down in the second. And you could see how it shifted by 1 carbon. So the ring flip will shift the substituents by 1 carbon. That's 1. 2 will also shift them from axial to become equatorial or equatorial becoming axial. But it will not shift the direction of the bond. If the direction of the bond is up, it's going to have to stay up. If the direction of the bond is down, it has to stay down. Now, in terms of stability, which of the two is going to be more stable? Well, let's see. Ethyl and methyl. Which of the two do I want to keep equatorial? The bigger group. Which of the two is a bigger group? The ethyl. So having an ethyl equatorial on this chair conformation automatically will have less 1,3-diaxial interaction, therefore more stable chair conformation. So this is important to keep in mind. How to draw a chair conformation requires practice. Draw the skeleton. Make sure that you are able to draw the one tilted to the right and the one tilted to the left. It's very important that you mimic how the structure, the skeleton of the chair conformation is drawn. That's the very first thing you want to practice. The second, be able to draw all the axial position bond and all the equatorial position bond. Third, the rule when it comes to chair conformation ring flip, the group that's axially positioned in one is going to have to go equatorial positioned in second. The one that's equatorial positioned in the first is going to have to go axial position in the second. The fourth rule, whatever positioned up in the first has to also positioned up in the second. Whatever positioned down in the first has to also position down in the second. That's how the rules are. And it's very important that we practice enough until we master how to draw a chair conformation. The last thing I want to talk about in this chapter is naming bicyclic systems. What does bicyclic mean? Having two rings that can be fused together, or having a bridge between them, or having a carbon, one carbon that would be the spirocyclic compounds example, having only one carbon holding the two rings. We're going to be responsible for the first two types, the fused rings and the bridged rings. An example of fused rings would be the first one, where we're going to see clearly that the two rings fuse together, having a bridge between the two. And that the bridge is basically what you see between the two rings right there. The other example, which is an example of bridged rings, where you're going to see clearly that you have two rings attached through a bridged carbon between the two. So that's the difference between fused rings and bridged rings. How do I name either of the two bicyclic systems? If I'm dealing with a bicyclic compound, that will always follow the following format: bicyclo, and opening brackets with 3 digits within the brackets, and ending the name with the alkane. What does this alkane parent gonna stand for? The total number of carbons in the bicyclo system. The total number of carbons. So if I have total number of 8, that means this alkane becomes octane. If I have 9, well, then it will become nonane. If I have 10, it will be decane. That's where the alkane come from. Bicyclo is due to the fact that it's a bicyclic system. All right. Now, how do we figure out the 3 digits going to go in the brackets? Well, this bracket is going to depend on the following. The first digit is going to be the bigger ring number of carbons of the bridge. So if I look at this structure, I have 2 carbons holding the 2 rings. Now, how many carbons coming off from each side? The one to the left, obviously it's the bigger ring. So how many carbons? 1, 2, 3, 4, and that's what goes first. The first digit is the bigger ring number of carbons coming off the bridge. And the second digit is the smaller ring. How many carbons coming off the bridge? So you can see clearly here that you have 1, 2. So that will be the second digit. The third digit, that indicates how many carbons off the bridge. So in this case, you have a fused bicyclic system. That's why the digit will be 0. You have no carbons on the bridge. Compared to the other bicyclic system, you could clearly see that you have a bridge here. So you're going to have the same thing. You're going to have a bicyclo, starting the name with the word bicyclo. The first digit will be the number of carbons coming off the bridge. So you have 3. So the bigger ring will go first. The smaller ring will go next. And the last digit will be the number of carbons on the bridge, which is in this case going to be 1. Octane will be the total number of carbons. So you have 1, 2, 3, 4, 5, 6, 7, 8. And that's why you have the word octane. So there will always be, the way how to name bicyclic system is by saying bicyclo, 3 digits, alkane. The 3 digits, the first digit will be the number of carbons coming off the bridge toward the bigger ring. The second digit, the number of carbons going toward the smaller ring of the bridge. And the third digit will be the number of carbons of the bridge itself. If there is no carbons on the bridge, then the digit will be written as 0. And the alkane will correspond to the total number of carbons in the bicyclic system. And that's the story of chapter 3.